This is sample 9-2 on page 379, conservation of momentum, a collision on ice. So we have two hockey players. One's initially moving and one is initially at rest. They're going to collide, and we're given some information about one of their final speeds, and we're going to find out some things about conservation of momentum. Now, this is a nice problem in one dimension only, so they can move, I'm going to say, to the left and the right. And we'll go from there. So our two items of interest, so we're going to call M1 Gordie, all right, I'm assuming they named this after Gordie Howe, who was a great hockey player from last century. His mass is 100 kilograms. He's moving, let's call this, I usually call it V1I. He's moving at 5 meters per second to the right. Okay, so I'm going to, just because they told me that first, I'm going to call that positive, all right? M2 is Mario, probably after Mario Lemieux. Somebody who wrote this book must be a hockey fan. His mass is 80 kilograms. His initial velocity is 0. Okay, so I have arbitrarily assigned M1 to Gordie and M2 to Mario. It doesn't matter, because at the end of the day, you're going to just tell me the answer I want. It doesn't matter which one's which. You just have to keep it separate in your mind. Okay. We're told that Mario's final speed then is 3.75 meters per second to the right. So I'm going to put that positive sign there, even though it's messy. All right. So what are the two questions we're asked for? We're asked for Gordie's final velocity. All right. After this collision, what's his final velocity? We're asked how much does Gordie's momentum change? And we're asked how much does Mario's momentum change? So the only formula that we need for this problem at first is conservation of momentum. And so conservation of momentum tells us that the initial momentum for both combined is equal to the final momentum combined, which means that P1I plus P2I equals P1F plus P2F, right? So we've got two objects, if you will, in our system, both hockey players. The only force that exists is the force that arises in their collision, their action-reaction pair. And so the total momentum before the collision is equal to the total momentum after the collision. And so how this usually breaks out is, since we have a one-dimensional problem, we can write it this way: M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. All right, now what is all of this, right? What is all of this? This is P1I. This is P2I. This is P1F. And this is P2F. All right, so we've broken out the momentum into some actual stuff that we can solve for, okay? What are we actually looking for? If you remember, we're looking for the final velocity of player number 1. So I'm going to do some algebraic manipulating here. It's ugly, but it's algebra 1, guys, so you absolutely can do this. M1 V1I plus M2 V2I, whoops, I forgot, minus, right? I got to get the M2 V2F over to the left-hand side with M1 V1F on the right-hand side. Now, to take it one step further, right, I got to get rid of the M1 on both sides. Okay, so V1F, and the algebra is messy in this unit. Be careful with your subscripts. Write neatly so that you can read it. Okay, M1 V1I, M2 V2I minus M2 V2F, all of that over M1. Okay, so there is a 0 in here somewhere. V2I is 0. Be mindful of your negative signs, because it absolutely does matter. What you get is V1F equals positive 2 meters per second. So if you were wondering, okay, if you were wondering in that collision, is Gordie gonna continue to go forward, or is Gordie gonna bounce off Mario? here's your answer. He's going to continue to move forward, which should make sense. Like if you were running at someone who is standing still and you run into that person, unless, it would be an unusual situation that you would actually bounce off of that person. Okay, especially with no friction. So my answer here then is his final speed is 2 meters per second to the right. Right? Your answer is never, just like in Unit 1, your answer was never positive or negative. It was always up or down, left or right, north or south, east or west. And it's the same thing in this. The velocity is 2 meters per second to the right. Now let's do something that's possibly even more illustrative here. We'll show that their change in momenta are equal, okay? So let's see, the initial momentum of player 1 is 100 kilograms times 5 meters per second, which is 500 kilogram meters per second, right? His final momentum is 100 kilograms times that 2 meters per second that we just calculated, which is 200 kilogram meters per second. All right, both positive, okay? I'll put that in there, but they're both positive. So what was his change in momentum for player 1? It's final minus initial. So his momentum decreased by 300 kilogram meters per second, which should make sense. It slowed him down when he hit Mario. So that should make sense. Let's figure out Mario's change in momentum. His initial momentum is easy because he was at rest. His final momentum is 80 kilograms times 3.75 meters per second, which is 300 kilogram meters per second. What was his change? Well, 300 minus 0 is a positive 300 kilogram meters per second. So what happened here, is that the change in the first object's momentum, right? They have equal and opposite changes. The magnitudes are equal, right? But the signs are different. So in this collision, who was first? Gordy lost momentum, Mario gained momentum, and the amounts of gain and loss were equal. Okay, so the momentum of the system remained constant. So we'll do lots more collisions, but this is a good start.